Good day. For those of you who do not know us, we're the instructional staff for EC 150, Professors Hiren Patel and Werner Dietl, and Douglas Harder. In this topic, we will give an introduction to the concept of recursive algorithms. So, in this topic, we will introduce algorithm design techniques in general and the idea of recursion. We will introduce 3 problems that have recursive solutions. We will describe the general approach of recursive algorithms and provide pseudo C++ code for the above described 3 problems. Finally, we will look ahead and see what's in store for the next 3 lectures on this topic. Now, previously, up to this point, we've simply looked at explicit algorithms for searching and sorting arrays. We are now going to look at a specific algorithm design technique. Now, an algorithm design technique is a general approach that can be used to designing algorithms to solve a myriad of different problems. So rather than being a solution to a specific problem, it is an approach that can be used possibly in different circumstances to solve possibly very different problems. The technique we're going to look right now is recursion, and recursion itself is also the basis for more advanced algorithm design techniques that you will be seeing in your second-year course on algorithms, specifically divide and conquer and dynamic programming. Now, the word recursion is derived from the Latin word recurrere. This means to run back. It is also the root for the word recur and recurrence. Now, a recursive algorithm implemented as a function, which is what we're going to do in C++, is one that calls itself within the function to solve a specific problem. So that is, you call a recursive function with specific arguments. Within the execution of that function, it will call itself, hopefully with different arguments, in a way such that when it gets a response to its call with those different arguments, it will be able to create a solution for the one you asked for with the arguments you passed it in the first place. The idea of a recursive algorithm is reasonably straightforward. It is an algorithm that solves a larger problem by first breaking the larger problem into smaller but similar problems, using the same algorithm to solve those smaller problems, and then using the solutions to those smaller problems to create a solution for the larger problem. Now, for this to work, there must be some point at which there are problems so trivial that they can be solved quickly without any recursive call. So these problems that are so trivial that the answer is immediate are called base cases. So for a recursive algorithm to work, the sequence of calls must ultimately result in a recursive call to a base case for which the solution is immediately available. Here's an example of a recursive algorithm. Now, in a company, an employee may either be a worker or a manager. A manager has direct supervisory roles over those directly reporting to that manager. Now, some managers are executives, others are senior managers, others intermediate, and furthermore junior managers. Now, all employees worker or manager other than the CEO report directly to one other manager within the company. Now, managers report directly either to the CEO or some other manager, be it another executive or a senior manager. But generally, the only worker who reports directly to the CEO is usually the CEO's personal administrative assistant. Now, this creates a hierarchy within the company where a group of workers will report to a manager. That manager may report to either an executive or a senior manager. That senior manager may report to an executive, and the executive may report ultimately to the chief executive officer, the CEO. So, let us assume the CEO wants to know how many employees will be attending the Labor Day celebrations. So the CEO will ask the CEO's personal administrative assistant as to whether or not that person is going. But the CEO is not going to ask everyone in the company because not everyone reports directly to the CEO. Instead, the CEO will only ask every single manager that reports directly to that CEO to relay how many employees under them will be attending. Each manager, in turn, then asks any worker reporting directly to that manager if they will be attending, and they will ask each manager reporting directly to that person to relay how many employees under that subordinate manager will also be attending. So each manager will pass down this request, and ultimately when each worker has responded, each manager will then pass that information back up to the CEO. So, for example, suppose here we have a corporate structure. We have the chief executive officer at the top. At the next level, there's the chief technical officer, the chief operating officer, the chief financial officer, and the vice president of marketing and sales. Now, in this image, a square represents anyone who has a managerial role, and a solid circle represents a worker. And you can determine which manager a worker reports to directly by just following the edges. So the CEO will ask the CEO's administrative assistant and each of the executives or vice presidents regarding this question at hand. They in turn will ask any managers underneath them who, if they have further managers underneath them, will further send that query. At this point, the workers will be able to respond. And now, at the lowest level, we know that in the first group on the left, there's a total of 4 individuals, including the manager, who will be attending. And in the second group, there are also 4 individuals. Now, over there at sales and marketing, we have a reasonably complete attendance. So 6 people are responding under that low manager, then 5, then 5, then 3. Now, at this point, the next level of managers can determine the total number of individuals beneath them that are going. So, in the first case, the manager would determine, well, one manager has indicated 4, the other has also indicated 4. That manager's administrative assistant is going, and that manager is going. So that manager will report 10. Similarly, every other manager at that level will have counted the total number of individuals who are going. Once these numbers are reported to the executive or vice president, then those individuals can count the total number of workers who are going who are beneath them. Finally, all of this information is conveyed to the CEO, and the CEO at this point now knows that 64 individuals in this company will be attending the Labor Day celebrations. All right. Now, you will notice here that every manager performs the same task. Each manager will ask those workers reporting directly to them if they are attending, and they will ask each manager reporting directly to them to perform the same operation on those subordinate to that manager, subordinate to the current manager. This process must, of course, end at some point. At some point, we're going to have a junior manager who only has workers that are subordinate to them. You could, in theory, come up with a fake company where Henry I is the CEO, and reporting to Henry I is Henry II, and Henry III reports to Henry II, Henry IV reporting to Henry III, and so on and so forth ad nauseum, but that is an artificial construct. That doesn't happen in the real world. In the real world, at some point, you're going to have the base case, and that will be a junior manager who only has workers that report to that individual. All right, this is an example of a recursive algorithm. Here's another example. Suppose that you know there's a file called finalproject.cpp somewhere on the file system on your computer. Now, you may have thought that you saved it in a particular directory, but it's not there. And so you must have saved it or moved it somewhere else, perhaps accidentally. So the question is, how do you find it? Now, normally every single file system has some sort of search mechanism, but let's assume that you just downloaded the most recent patch and this caused that to fail. So how would you do this manually? So how would you systematically search through a file system to find a missing file? You would start in the root directory, and where that root directory is depends on the file system you're using. Now, in some cases, you may call a directory a folder. Sure, that works as well. However, essentially they're the same thing. Now, you first check, is the file in this root directory? If yes, we're done. We have found the file. If not, we can start visiting this directory's subdirectories alphabetically one by one. Alternatively, of course, you may start visiting the subfolders alphabetically from the given folder one by one. But from now on, we're just going to call them directories. We will use the exact same approach for searching each of these directories. Now, if there are no further directories to search in the current directory we're looking at, we will then go back up one level in the directory or folder hierarchy, and we will continue searching in the next directory that is in alphabetical order, if any. So perhaps you can see too that this is another recursive approach. For every single directory, we search the files that are in that directory, and if we don't find it, we then start searching any subdirectories. And we will search those subdirectories in this same approach. Ultimately, you may deduce that we will have searched every single directory within a particular file system. All right, this is another example of a recursive solution to a specific problem. So once again, note that the searching of every directory is exactly the same. Inspect the files in the current directory, and in a similar manner to searching the current directory, we're going to search any subdirectories, and we will do so in alphabetical order. And this must end at some point. There are going to be base cases, and the base cases are those directories that only have files in them, no further subdirectories. So here's another example. Interestingly enough, 5 in 1,000th of this world's population is a paternal descendant from Genghis Khan. So, you are a paternal descendant of Genghis Khan if either you are Genghis Khan himself or your biological father is a paternal descendant of Genghis Khan. That, as you can see, is a recursive description. Well, are you a paternal descendant of Genghis Khan? Well, you are probably not Genghis Khan, so you'd determine whether or not your biological father was a paternal descendant of Genghis Khan. How do we know if he is? Well, we would ask that person's father, biological father, if that person was a paternal descendant of Genghis Khan, and so on and so forth. So how do we describe someone who is not a paternal descendant of Genghis Khan? Well, there are different ways, and it's a little bit more difficult to describe, but not too hard. You are not a paternal descendant of Genghis Khan if either you were born prior to 1155 CE, the year Genghis Khan was born approximately, or your biological father is not a paternal descendant of Genghis Khan. So if either of these is true, then you are not a paternal descendant of Genghis Khan. So, for example, if perchance you are able to trace your paternal lineage all the way back to Hassan II of Alamut, then you are not a paternal descendant of Genghis Khan. Thus, a problem can be solved in a recursive manner if there are some problems that are so trivial to be solved that they can be solved immediately. These are called the base cases, and in the 3 previous examples, the base cases were first, managers who only had workers reporting directly to them, directories that only had files and no subdirectories, and finally, individuals who were either Genghis Khan or born before 1155. It is therefore also necessary for a problem to be solved recursively if any other problem can be solved by solving similar but more simpler problems using the same algorithm and then using the solutions to these simpler problems to solve the current problem. Now, the structure of a function that implements a recursive algorithm can generally be written in a common manner. First, we have a condition that determines whether or not the current set of parameters describes a trivial case. If the current set of parameters do describe a trivial case, then we solve that trivial case and return the appropriate value. The alternative body is the recursive case. So in the alternative body, we will determine appropriate arguments that describe a simpler situation, and then we will recursively call the same function with those arguments. We will then possibly collect the solutions to these subsequent recursive calls and use these solutions to solve the current problem. Now, the next 3 slides will use pseudo C++ code to show how we could program the counting of the number of attendees from a particular company, finding a file in a directory structure, and checking to see if you are a descendant of Genghis Khan. So here is pseudo C++ code for a function called count attendees. We start by having a local variable count that is 0, and then first the manager determines whether or not that manager's self is going. If so, increment the count by 1, and then the manager must discuss this with every single worker that reports directly to that manager if that worker is going, and if the worker confirms, then the count will be incremented. Now, the base case is if there are no managers subordinate to the current manager, in which case we simply return the count. If, however, there is at least one manager subordinate to the current manager, then for each manager reporting to this particular manager, we will add to the count whatever that manager responds when you recursively ask them to count the number of attendees. Having added up all these numbers together, then the count attendees function returns the total count. Here's the pseudo C++ code for searching a file system. We will pass the find file function a string, that is the file name in question, and we will return a string. If we do not find the file, we will return the empty string. If we do find the file, we will pass back a directory path to the directory storing the particular file that we have found. All right, so we start by simply searching the current directory. Did we find the file in this directory? And if so, then we're just going to return a directory path to the current directory and we're finished. Suppose that we don't find the file. So now we have the base case. If this directory has no subdirectories, we immediately return the empty string and we are done. If, however, this directory does have subdirectories, then for each subdirectory in alphabetical order, we will ask that subdirectory to attempt to find the file, and we will recursively pass on the file name, and we will get that result, and it is stored in a local variable called result. Now, if a particular subdirectory did not find the file, it will return the empty string. If it did find the file, it will return something other than the empty string. So, if the result is not the empty string, that means that we actually found the file in question, so we will return that directory path as a return value for the current function as well. If we have searched all of the subdirectories and all of them have returned the empty string, then this function will also return the empty string. So, finally, here's pseudo C++ code for determining if someone is a descendant of Genghis Khan. So, if I was born prior to 1155 Common Era, then return false. If, however, I am Khan, then we will return true. And both of these are the base cases. As we can see, there may actually be very many base cases, as there may be very many people born prior to 1155 Common Era. The recursive case is to check if the biological father is a descendant of Genghis Khan. Alright, now however we implement that may be a problem, but at least this gives you the approach. We have the base case, the first two, and the recursive case, which is the alternative clause. Now, the next three topics are going to cover first mathematically recursive functions, because these are functions that you are already familiar with. We will then look more extensively at engineering problems that can be solved using recursive algorithms, and finally we will see how the call stack supports recursion. So, following this topic, you now have an idea as to what an algorithm design technique is, and you understand the idea of recursive algorithms for solving problems. Not all problems can be solved recursively. However, we have seen 3 examples where we have a problem that can quite reasonably be considered to be solved recursively. We then saw the standard structure of what a function may look like if it is solving a problem recursively, and we gave you pseudo C++ code to solve the problems we discussed or described earlier in this topic. Now, these are more real-world abstract problems that could potentially be solved recursively. In the next few topics, we're going to look at explicit problems that we will find explicit recursive solutions to solve. First mathematical, and then more general. Here are the references, acknowledgements, the colophon, and a disclaimer. Cheers!